Hello and welcome to our discussion on summary statistics. What I would like to do in the next half an hour or so is to talk about three different things. First of all, I want to share with you some of the common questions that come directly from the summary statistics topic that could be found on standardized multiple choice type exams. Secondly, I'd like to show you how a box plot is made. So if you already know how to do that, you can skip that part. And then also, I'm going to show you how standard deviations are calculated using some examples out of the textbook. So let's go ahead and get started with the common types of test questions. And the common types of test questions we actually touched on previously have to do with pictures and numbers that are used to summarize a collection of data numbers. So if you have collected a sample, for example, and you want to summarize that information either as a picture or as a set of numbers, then that's what we're talking about in this video. So the kinds of questions that you get for this particular topic is given a specific variable type, and that's in this particular column. What kind of picture would you create to show a summary of that particular variable? Or given a particular variable, what sort of numbers would you use to summarize? Now, last time as a quick review, both nominal and ordinal variables are categories. Nominal are categories that are not in order, and ordinal are categories that are in a specific order. What we found is that the picture that we'd like to create for that scenario would be either a bar graph or a pie graph. And I'm sort of lumping them together here because very often we treat them both the same. And I'll show you a situation here in a minute where we don't treat them the same. If we have a scale variable, and that would be something like age or height, weight, all those kinds of things that have units of measure, then the kind of thing that we use for that is commonly, the most common is a histogram. And then you also learned about stem and leaf plots, which technically are not pictures. They are a collection of numbers, but if you look at them a certain way, if you tip your head to the side, then you can see the shape of the distribution. So I count it here under pictures instead of numerical summaries. The thing that I would like to add to this particular collection of variable types is that there is actually something here in between that deserves its own category. And this happens when we either have a scale variable that's demoted or an ordinal variable that's permoded. And by a scale variable that's demoted, what I mean is that we have a scale variable, but it is not normally distributed. For some reason, I'm going to just put that here as an ND. So not normally distributed, that's sort of like shorthand. That could be not normally distributed because it's skewed, or it could be not normally distributed because there are some outliers there. And so we sometimes will create a different picture, the pictures here, because of that not normally distributed feature of that scale variable. The other scenario is where we have an ordinal variable and it is permoded to be like these scale variables that are not normally distributed. And the specific case that we use that is if we have an ordinal variable that has many values, and I'll just put MV here. And the specific definition that I'll use for many values is one that's commonly used by a lot of statisticians, but it's not a hard and fast rule. By many values, what we mean is that we have an ordinal variable, in other words, they are in order, and there are 8 or more categories. So I'll just put in parentheses here 8 plus cat. And the thing about 8 plus categories is that that variable starts behaving a little bit more like a scale variable, although it doesn't get all the way to that scale variable. So it's promoted to this kind of in-between category, and I very cleverly made it green, which is a combination of yellow and blue. So here's our yellow and here's our blue. So you can think of this as sort of an in-between ordinal and scale category. And the kind of picture that we make for that particular category of variable is called a box plot. It might also be called a box and whiskers plot because it does look like a box with whiskers sticking out of it. So for now, that's the main thing that I'm going to be telling you about box plots, but later on I'll show you exactly how to create one. So for that middle category, it would be a box plot. So if we go back to the whole idea of what kind of questions could be asked on some kind of a multiple choice, like maybe your CBH exam or even your quiz, basically that will be phrased as they'll give you a scenario of one of these three. So it'll be a scale, or it'll be this middle category, it'll be nominal or ordinal. They'll say, given a specific variable, they might say age, or they might say education level, what kind of visual representation would you use to represent that? And these will be the different possible choices: stem and leaf, histogram, box plot, bar graph, pie graph. So they will not necessarily say that it's a scale variable. Given a scale variable, what picture would you make? They'll give you a scenario, so you have to make that step in between. You have to be able to take that variable, know what kind of variable it is, and then know what kind of picture to make for that type of variable. So there are a couple of steps to that kind of a question. The second piece, let me go ahead and just kind of draw some lines across here so we can follow this a little bit easier, is what kind of summary statistics, or these numbers, would you use for each of those different types of variables? And before, we learned that for numeric variables, we would use a mean and a standard deviation, and those two go hand in hand. We use them together. For these categorical variables, we learned that we would use n and percent, and I'll show you an example of what that looks like. And then most commonly for this kind of middle ground area, for that we would use median, and I'll just abbreviate it MED, and interquartile range. Those two go hand in hand. When you see median, think interquartile range. Now that's not a hard and fast rule. You could use median with range. Some published articles use mean and variance. And so these are just the most common, but this is the kind of thing that you'll see on testing. So if you remember, mean is just the summary, or the mathematical average of all of the numbers added together divided by n. Median is the middle value, and n is the count for each category. And so sometimes we think the largest category then would be the mode. That's not usually the thing that's reported, but that is some information that we could get from that. We could look at those different categories and say which one is the largest. So that particular question would be worded, given a specific variable, what summary statistics would be best to represent that, or how would you represent that in numeric form, something like that. And here are generally the choices: mean and standard deviation, median and interquartile range, n and percent. The mode really isn't something that we generally report, so that is just something that you would notice based on the fact that that particular category was the largest. So those are your choices for that particular answer. And so again, you have to take these particular variables and you have to turn them into, you have to know what the variable is and figure out what level of measurement that is, and then you have to know for that level of measurement which particular summary statistic you would use. So those are some very common questions. The third typical question that comes from this general area has to do with the idea of skew and how that affects this mean, median, and mode. And so let me go ahead and draw what that looks like. We're actually going to ignore this whole words section for now. We aren't really addressing that, but that is one way that we report things. So in terms of normally distributed variables, let's just draw something here, and this is supposed to be symmetrical. Sorry if it's not exactly. But here's an example of a normally distributed variable. It should be a mirror image around this middle line, more or less, if we consider it to be normally distributed. And if it's normally distributed, then what we found is that mean and standard deviation are good representations of that information. Now, what happens when that's no longer normally distributed? And let me go ahead and show you what that could look like. We might have something that starts out looking like it's normally distributed, but then the tail heads off in one direction or another. Now, the bottom line for this type of a question is that they'll say, if a variable is right skewed or positively skewed, what effect does that have on? And then they may say something about the mean or the median or the relationship between the mean and the median and the mode. So here's how that works. If a variable is normally distributed and it does not have skew, then the mean, the median, and the mode are all in the exact same location. As soon as you have positive skew, and this is skew in this direction right here, where the direction of the tail says where the skew goes, then the peak is the mode, the median is shifted to the right, and the mean is shifted even more to the right. So as soon as you have skew, you can imagine somebody just grabbing onto this tail and pulling it to the right. So that's called positive skew or right skew. That also shifts the median to the right and the mean to the right. And so if you have positive skew, the mean is larger than the median. These are all different ways that particular question could be asked. Similarly, if you have something that is very left skewed, or it kind of got pulled in this direction, the mode will be to the right of the median, and that will be to the right of the mean. And so both of these got essentially shifted to the left in that particular distribution. And depending on how severe the skew is, will decide how much those different measures of central tendency got shifted to the left. So that is a very common type of question that we'll see. The mean is typically affected more than the median in that particular case. So those are the three typical types of test questions that come from this specific material in Chapter 4 of your textbook. If you already know how to make box and whisker plots and you know how to calculate standard deviation, then the remainder of this video wouldn't really probably be helpful to you. If you'd like to watch me draw those, then I will go ahead and do that now. So what I'm going to do is I'm going to take an example out of your textbook on page 86. Near the bottom there is something labeled Illustrative Example. And in this particular example, we have a small ordered array, in other words, a collection of numeric values that are arranged in order from lowest to highest. And these are values of air quality. They were air samples, and something was measured in micrograms per cubic meter. And the specific numbers that we have here are 5, 11, 21, 24. I could draw them all on here if you needed them to be. Why don't I go ahead and do that? 5, 11, 21, 24, 27, 28, 30, 42, 50, and 52. And so what we know about the box plot is that we need to find some specific things in this data set. First of all, we need to find the median. That's going to be our middle value. And since we have 5 values over here on the left and 5 values over here on the right, the median is actually in between 27 and 28. So we calculate the average here, and the median is 27.5. Then we need to find the middle value of this left group. 1, 2, 3, 4, 5. The middle value is here at 21. And we also need to find the middle value of this right group, which is the middle value of 5 again, which is 42. Now, this left value is called quartile 1. The right value is called quartile 3. And that's because what we've tried to do is we've tried to separate this into 4 even quartiles, or 4 even groups. Now obviously this is a really small sample, but you get the general idea. There are 4 sections, and so this is the cut point between quartile 1 and 2. This is a cut point between quartile 2 and quartile 3, which is also known as the median. Here's the cut point between quartile 3 and 4, and then you have your lowest and highest values within this particular data set. So using all 5 of those data points, we are now going to create a box plot. And when you have the computer do this for you, it's even easier. So I'm going to just put some numbers on here: 10, 20, 30, 40, 50, 60, 70. I realize I'm going higher than the data set goes, and that's for a reason. I'm going to go up here to 80, 90, 100, because we need the value 105 eventually. So in order to graph this, the first thing I'm going to do is I'm going to go ahead and put this central value, 27.5. And I'm going to find where I think 27.5 is, and scroll over, and then I'm going to put a horizontal line. It doesn't matter how wide it is, this is going to be part of the box. Then I'm going to find this low value right here, 21, and that's right about here. And then also I'm going to go across and find that value, make the bottom part of the box. And then this top value, or 42, which is right about here. Let's go on over, and then actually I should probably make that in a different color, but it's all right. So this now is my box plot, and this is the box part of the box plot. And the box plot gives you a sense of how that information is distributed. If you were to tip your head to the left so that you're looking at that box, what you'll notice is it's very much like a histogram. And so here we have the peak of the histogram, and then kind of like the middle half of that data. So that creates the box. The next thing that we do is we go to our lowest and highest values. And there are a few exceptions I'll tell you after I finish making the graph. I'm going to go here, and I'm going to plot number 5 as a little dot, and I'm going to plot number 52 as a little dot. And my box plot then is going to go from here. This is the whisker part. I make a little dashed line so I can see the whisker sticking off. That is my completed box plot. So that's how you create the box plot. Now the only exception to that is that sometimes if there's a value out here at the end, or multiple values out here at the ends that are too far away from the box, we might plot them as little circles, or we might plot them as X's. And the little circles represent outliers, and the X's represent what are called extreme values. So let's say, what if this highest number here, instead of being a 52, let's imagine that being an 82. And so that 82 is way up here. See how far away from the box it is? The technical calculation for an outlier is that it is more than 1.5 widths of this box away from the top of the box, or it's more than 1.5 widths of the box away from the bottom of the box, somewhere down here or somewhere up here. So let's go ahead and calculate this interquartile range. The interquartile range is equal to 42 minus 21. So here's our low value and here's our high value. So that is actually equal to 21. So if we were to say it needs to be more than 1.5 of this box width away, that is 21 times 1.5, or that's equal to 31.5. If we start here at 42 and we add 31.5 to that, what that tells us is that anything beyond, and I'm going to draw this with a black line, anything beyond about 73.5 is considered to be an outlier. So this new value, like what if this value was 82 instead of 52, that would be considered an outlier. And my whisker in that case would only extend to 50. And so my whisker would end here instead, because that is my most extreme value that's within what is called the fence. So that helps me decide if something is an outlier, and this is supposed to be a circle that has a hollow part in the middle. I'm just drawing with a clumsy pen. So that creates my outliers. Unless I have negative numbers, I'm going to have a hard time creating outliers below the box and whiskers plot in this particular case. So that's what an outlier looks like. I told you that there could also be extreme values, and an extreme value, let me go ahead and draw this maybe in another color. An extreme value is something that is more than 3 box plots, 3 times the width of the interquartile range away from either the top or the bottom of this box. And so that would be 21 times 3, which is 63. So 41 plus 63 is 105. So let's go ahead and draw a fence here, right across at 105. So if this number, instead of being 82, was actually 122, that would be considered to be an extreme value, and that is marked by a little X. So sometimes you'll see several little zeros, and then there will be a couple of X's that designate your outliers and your extreme values. So that's what you'll typically see on box plots, and that's how you create one. The next thing that I would like to show you is how to calculate the standard deviation. So for this, I'm going to be using an example on page 91. I think I misspoke. I think this is actually the air quality example. Yes, it is. At the bottom of page 91, we get a visual of these 8 data points, and since they're on across on a graph, it makes it easy to put them in order. So let's go ahead and do that. And these represent some air samples from this particular page, and they are in micrograms per cubic meters. So here we have, there's a 32, 33, 34, 36, 36. Notice how there are 2 little circles there, 38, 39, and 40. So those are our 8 data points, and we're going to calculate standard deviation from this. The first step to calculating standard deviation is actually to calculate the mean. So what we have to do is we have to add up all those numbers. We get 288, and then the mean is equal to the 288 divided by 8, because there are 8 numbers here, n equals 8, and so that equals 36. So our mean is going to be the thing that we put in our next column. So these are the actual values. I'm going to put 36 here for all of the different values, and you'll see what we're going to do with this pretty soon. 36, 36, 36. We're going to compare each of these values to the mean. We're going to see how far away it is. And the way to do that is to calculate the difference, what's called the difference score. And so if I take 32 minus 36, I get a difference of -4. If I take 33 minus 36, I get a difference of -3. Here we have -2. The difference between 36 and 36 is 0. 38 minus 36 is 2. 39 minus 30, oops, I wrote a 3, sorry. 39 minus 36 is 3, and 40 minus 36 is 4. So here we have all our difference scores. Now, the thing that you should notice about the difference scores is if I were to add them all up, I would get a big fat 0. And so that's not very helpful, right? In fact, that's the very definition of calculating the mean, is that the difference scores should add up to 0. So if we're going to try to figure out something about spread, we have to do something else, not just the difference score. And what we end up doing is called the difference squared. So we take the difference and we square it. So -4 squared is 16. -3 squared is 9. -2 squared is 4. 0 squared is 0. 2 squared is 4. 3 squared is 9. And 4 squared is 16. So you'll notice now all of these numbers are positive numbers. And if we add all of those up, we end up getting 58. Now, in order, see how over here we actually divided by the total number of values that we measured? In order to calculate the variance, what we have to do is we have to take this 58, and instead of dividing by 8, which is our number, we actually divide by n-1. And n-1 is 7 in this case. So 58 divided by 7 is 8.286. And the problem with this number is because we squared it, this is in micrograms per cubic meter squared. So our units are different than our units for the mean. This is in micrograms per cubic meter. So, since this is squared, in order to come up with something that's a useful number, we have to take the square root of that variance, and that's what standard deviation is. So standard deviation is equal to the square root of variance. So in this particular case, it's the square root of 8.286, which is equal to 2.88. And the magic thing about that number is that it now is in micrograms per meters cubed. So now these two numbers, our mean and our standard deviation, are on the same scale. And that's actually important when you're trying to draw some kind of a picture or creating summary statistics. So here we have a mean and a standard deviation, and if we were to draw the histogram that goes with that, the mean would be here in the middle, and the standard deviation is actually somewhere about yay far away from it, both above and below. So if we were to take this information, the 2.88 and the 36, and go back to our original table, remember how we said for numbers, we report this as mean and standard deviation. So this, in this case, we would say the mean is 36 with a standard deviation of 2.88. And we would put the units on there, but I don't have room right here. In terms of the box plot, if we were to take the information from our box plot that we created, assuming that we didn't make these odd changes here, the median is 27.5 and the interquartile range is 21. So 27.5 and 21. Let's go ahead and put that on here, 27.5. And this you typically have to write out because there's not a standard notation. Interquartile range is equal to, did we say 21? So that's what those numbers would actually look like in a table. So we want to take the information that we create and actually be able to report on it. Now notice that these summary statistics, the mean and standard deviation, or the median and the interquartile range, don't really give you the whole entire picture. And so it's always really important to also include a picture when you're reporting summary statistics like this. So let's do one last thing and fill in this graph, or sorry, this chart for the bottom section. And the way this would look is, like, for example, let's say that we do have some kind of a categorical variable. I'll use education. And so then let's say we have 4 categories up to high school, graduate, maybe we have up to associate, maybe up to bachelor's, and graduate school. And we need these to be exclusive categories, separate from each other. And the way this would look in an actual table is, and you've probably seen this, is for this category, let's say we have n is equal to 100, maybe the associate degree would be 150, bachelor's degree might be 200 people, and graduate could be 50. What you'll normally see then is the percent of total in parentheses. So this would be 100, which is 20%. 150 would be 30%. 200 would be 40%. And then 50 would be 10%. So those percentages for all the categories should add up to 100. And that's just what you would see in some kind of a summary table. So that concludes our discussion on summary statistics. Thank you for joining me.